So, hi there. My name is Marc Greenberg. I'm Product Marketing Group Director at Cadence, responsible for DDR, HBM storage, and MIPI IP. And today I'm going to be talking about compute in memory. And it's a topic that a lot of people ask me about. They say, hey, what's happening in the compute in memory space? And I thought what I'd do is give a little introduction, a little primer to what compute in memory is. So, if you think about a standard system, we have a CPU and connected to a memory that's outside of the CPU. And let's look at a simple function that we might do in computing, like y equals y plus x, which I do with all kinds of things like a loop counter or accumulating something, all kinds of stuff that I'll do with a very, very simple function. And if I look at what I have to do, so I've got y out here in memory at address A. So I've got some address A that has the value y stored in it, and I've got x over here in the CPU. And I've got to do y equals y plus x. So what do I have to do in a traditional system to accomplish y equals y plus x? Well, the first thing that I have to do is I have to send over here a read transaction. So I'm going to send a read transaction of address A. And then, so I'm pushing a transaction across this interface, across a PCB, which takes energy to do that. And then I'm going to get the value of y back. So y is going to be transmitted back across the bus. And so now I've got x and y both here in the CPU, and I can do x plus y, and I get a new value of y, which we'll call y prime. And then I need to send it back into the memory. I need to put it back into its original location. So again, I need to send another transaction. I need to send a write transaction, which is write to address A. And then I need to send the data, which is the new value of y prime. And then I've updated my memory now so that I now have y prime stored in memory. And that's a lot of operations to do a really simple function, right? So I've had to move data. I've had to send two commands across the bus, and I've had to move this data all the way over here and then move it back again. And all of those things take energy, and they also take time, and they take the attention of the CPU. Right? So the concept of compute in memory is that perhaps maybe I could make the memory just a little bit smarter. And so instead of having a memory that can't do anything other than store values, what if I could have an accumulator function inside of the memory? So instead, what changes? So now I have if I change this, so I now have a compute in memory. Right, so I have my value x over here, and I want to do y equals y plus x. So what I can do is I can send a single transaction, which will be accumulate. Let's call it accumulate. We'll call that accumulate A, and I'll send the address that I want to accumulate, and then I'll send a transaction with a data value with it, which is going to be x. And then over here in this memory, it internally will do the accumulate function on x, and so I end up now with y prime in the memory, which is what I wanted. But I only had to move half as much across the bus in doing that. So I was able to move, by putting a very, very simple logic function out here in the memory. I'm able to reduce the amount of transactions going across this bus, these very expensive transactions in terms of energy. And reduce those by half. So that's a great idea. So why is not everybody doing it right now? And there's some good answers for that. So the first thing is the memory dies themselves are really, really bad at doing logic functions. They're optimized for one thing. On a typical memory chip today, I'm going to put down 4 billion or 8 billion transistors. I'm going to sell that for $4 or $8 if I'm a memory vendor, something like that approximately. So that process is really, really optimized for doing that one function, which is the memory function. When you start trying to put logic in here, it doesn't really function very well. The area is quite large, and the cost of putting those simple logic functions into this memory are quite high. And then the other thing to remember, we look at this as hardware engineers, and we say, well, this is a good thing to do. Computer scientists would look at this in a slightly different way. They would look at this and say, well, first thing that I can do is not have y out here in this other memory at all, right? So a computer scientist would look at this and say, you know what? I'm just going to keep y over here on a cache on the CPU, and then I can just increment it whenever I want, and I don't need to move it across the bus. So that's something that a compiler would do if it recognized that y was going to get updated a lot. It's actually just going to keep it on the CPU die. Even if the cache is full, what I may still do is I may have y out here in memory, but what I can start to do if I know that I'm going to touch it a lot is I can do successive loop transactions. If I'm doing this y equals y plus x a whole bunch of times, I'll just start accumulating values of x inside my cache on the CPU, and then only one time, sometime much later, I'll transfer that and then do the x equals x plus y, or the y equals y plus x function over here in the memory at some later date. So I've got a lot of options that I can do without actually having to do the computing in memory. So that's kind of where we are. I wanted to give you a quick introduction of what compute in memory is. It's basically putting logic functions inside the memory and being able to reduce the transactions across the bus from the CPU to the memory. But we're not fully there yet in the industry. There's still a lot of things to work out, and there's a lot of smarts that happen within computer scientists and compiler folks that relieve the need from having to do that. So will it happen one day? Maybe, but we're not quite there yet. So that's my Whiteboard Wednesday. Tune in again for more.